The topic of the panel will basically be to cover, so all of the people that are joining me here today are actually funded and represent institutions that are funded from Quantum for Bio. And their particular topic and their particular projects are actually in the area of applying quantum machine learning, or maybe machine learning with some quantum inputs, let's say, to biological and health-related problems. So I would like to really give an opportunity to all of them to introduce themselves. And briefly before that, so Quantum for Bio is a $50 million program funded from Wellcome Leap. We are now in the first year when we have already 12 teams on board, and they're all looking at different applications that are relevant to human health. And it's very important that it's kind of developing algorithms for, let's say, early fault tolerance quantum computers that can improve health applications. So without further ado, Kanav, can you please introduce yourself?
Yeah, sure. Hi, everyone. My name is Kanav Setia. I'm a co-founder and the CEO of qBraid, and we're super happy and excited and thankful to Wellcome Leap for having given us an opportunity for the grant. So our proposal is called QuantaBind, and what we're trying to understand from the healthcare perspective is the problem with Alzheimer's and Parkinson's. So the proteins that play a role in Alzheimer's and Parkinson's, there are two kinds of proteins, beta amyloids and alpha-synuclein. And what we wanted to study is the binding sites on those. So these interact with heavy metal ions to form these plaques, which are markers for many of these diseases. And so the goal is to develop quantum techniques to break these giant proteins into smaller chunks. So we use classical techniques for those. And once you get to the fragments, you recognize the fragments which are hard classically and easy classically. So the easy parts go to classical computers. The fragments which are hard classically, you send it off to quantum computer. And on quantum computer, we do another set of fragmentation techniques which are purely quantum in nature, and you break them further and you simulate on quantum computers. And sort of we're aiming to build this nice pipeline that allows you to get better energies or better understanding of these protein molecules.
Before we're moving forward, can you say something about the team, actually, and the composition of the team?
Yeah, absolutely. So we're leading the grant, and we have teams from University of Chicago, Professor Laura Gagliardi, who's a well-known chemist at University of Chicago, and then we have Professor Troy Van Voorhis, who's head of chemistry at MIT. And so Professor Laura Gagliardi is going to focus on something called LAS-UCC, Local Active Space Unitary Coupled Cluster, and they have these fragmentation techniques. Another fragmentation techniques is being developed at MIT, which is called quantum bootstrap embedding. And both of these techniques are going to use something called generalized superfast encoding, which is what we're developing at qBraid. And the way it happens is fragmentation techniques get developed at these universities, and then we have these superfast encoding, which allow you to map a fermionic system to a quantum qubit system with inherent error correction in them. And then we're going to take that and simulate it on quantum computers, which will be available in a couple of years.
Thank you.
Okay, hi. I'm Grant Rotskoff. I'm in the chemistry department at Stanford. Our team doesn't have a catchy name, unfortunately. We'll have to work on that. My background is more in sampling high-dimensional systems like proteins and understanding their fluctuations, and that's actually a problem that is studied quite a bit from the quantum perspective. However, what we saw was an opportunity to actually study chemical dynamics more directly, and in particular to look at enzyme catalysis in situ in proteins. And to sort of build up the technology for this, we're using a combination of energy calculations done on eventually, hopefully, quantum computers using variational quantum eigensolver techniques. and then integrating those into a machine learning pipeline to build potential energy surfaces on which we can run ab initio dynamics. So this is kind of set of technologies that we've been building up over the last several years, and I think they're starting to overlap at the point where we can actually use them productively to study chemical dynamics at accuracies that are not accessible to most modern electronic structure theories. So that's sort of the overarching goal of the program, and the team kind of has expertise that spans all of these different topics. So we have Norm Tubman at NASA, who has been developing a lot of the VQE approaches and also has developed simulators of quantum circuits that can kind of scale well beyond what we can do with exact simulators. So he has a couple of good judicious approximations that he can use. And in addition to that, we have people who have expertise in electronic structure at Brown University, Brenda Rubenstein, people who have been developing methods to compress the inputs to VQE so that we can actually put realistic Hamiltonians on quantum circuits. So that's Ryan LaRose and Sofia Economou and Wojciech Wilczek, who are all over the place. So it's a combination of academic labs, national labs, NASA, and me. So that's the team.
Thank you. Iordanis.
Hi everyone, thanks Elica. My name is Iordanis Kerenidis. I'm a senior VP for Ware on quantum algorithms. I've been working on quantum algorithms, as I want to say, since last century, so almost 24 years now. It was a very different field back then, but yeah, we're really excited working on more practical use cases now, in particular in this Wellcome Leap project. So you got some details at the talk before by Ivona. We're working on MRI-based diagnosis. And the team, apart from QCware, includes Roche and also Matthew Rosen from the Harvard Medical School and from the Mass General Hospital, where he's one of the world experts on MRI and low-field MRI. So we're really excited to understand the process of how MRI machines work. There's a lot of quantum effects, you know, in the censoring part of how you get, you know, the information out of our body and try to make it into an image that the doctor can, you know, can see and be able to make a diagnosis. So throughout this pipeline, we're trying to enhance these AI techniques by understanding these quantum effects and putting quantum machine learning on top of it in order to both make the diagnosis more accurate, but also try to do things like making the cost or the time that the patient has to be inside the MRI machine much less, for example. Like one of the main problems with MRI is not that we cannot make the diagnosis at the end, is that it's very expensive and a patient has to spend even 40 minutes within the machine. So we don't use MRI as much as we could because of these reasons. So the question is, can we get better methods of reconstructing, you know, the image from the MRI, and hence reducing both the cost but also the discomfort that for the patients. So yeah, this is our project.
Thank you, Iordanis. And last but not least, Tommaso.
Thank you so much, Elica, first of all, for the kind invitation. It's really a pleasure to be here. Unfortunately, I cannot see you because the lights are so strong, so we are just guessing that there is a really large audience. Another thing that I want to anticipate is that I hope that we do not say anything wrong, because in a few days we will have the quarterly review of the Wellcome Leap project. So I hope that what we say here will stay here. Is that correct, Elica?
Yes.
Can we count on that? Okay, excellent. So my name is Tommaso Macri. I'm the executive account manager at QuEra Computing. I also have an academic background, and until a couple of years ago I've been a physics professor. Then I decided to move to Boston, first for a sabbatical at Harvard, and then I joined QuEra in August last year. It's really an exciting path, I think, working together with the Wellcome Leap organization. We are really lucky to be part of actually 3 different Wellcome Leap projects. The one with Kanav that is led by qBraid. So thank you so much, Kanav, for the very nice introduction. And then we are also involved in another couple of other 2 projects, one which is led by the University of Nottingham, in collaboration, in partnership with a British startup which is Facecraft. And we have here one of the co-founders of Facecraft, Toby Cubit. So perhaps for those who are interested in really digging a little bit more into the details of their algorithm development, please feel free to reach out to Toby. And for this specific project, what we are looking at are basically the study of what are called covalent inhibitors for a specific, which are inspired by a very well known genetic disease, which is myotonic dystrophy, which is one of the most unfortunately popular genetic diseases that affect muscles. And the goal there is to study these small molecules that can really be that are basically can act as ligands to larger proteins that are relevant for the development of the disease in the individuals. So one of the goals there, from the theoretical and then the experimental implementation on our side, is really to understand at the level of QMMM type of approaches, so quantum mechanics, molecular mechanics approaches, basically the active space of these larger molecules, and then break down essentially what are called the active space, so the smaller part, and try to understand and develop both typical quantum chemistry algorithms as well as quantum computing algorithms that efficiently encode the properties of that molecule in such a way that we can then deploy those algorithms on real hardware. And that is precisely the part that we are developing at QuEra with a special hardware that is based on our neutral atom platform. Let me just comment on the last project, so I don't want to spend too much time on that. We are involved on another project that is led by Misha Lukin at Harvard, together with MIT and other collaborators from Argonne, for example. And there, the goal is to study really hybrid approaches, analog digital, to basically, again, study relatively small molecules that are relevant for other certain types of co-development of drugs. And also in this case, the goal of QuEra is basically to efficiently implement certain types of quantum algorithms that are basically inspired by drug discovery approaches. So with this, I will pass the word again to Elica.
Thank you. So this is a subset of the projects in Q4Bio. I would say 1/3, more or less. So there is a lot of activity. It's really exciting. And in fact, the projects cover everything from drug discovery, as we heard, to diagnostics, maybe also understanding protein structure and protein function. So it's really, really amazing. And I can't wait to see the outcomes of your projects. And now I actually wanted to ask maybe Iordanis, because he's really one of the leaders, let's say, in quantum machine learning. What kind of data do you think, he looks a bit scared, what kind of data do you think is best suited, let's say, to quantum machine learning algorithms and analysis? And how did you choose that particular MRI analysis, data for your project?
Yeah, it's a very good question. So if we try to understand as you said, what type of data, what type of problems we should look at quantum machine learning instead of just machine learning or something. So I think one case where it makes at least sense to start looking at is where we're looking at a problem where there are quantum effects happening, right? So I think many of the projects here, they have to do something with either molecular systems, that there is a quantum behavior there. We're trying to understand some properties of the systems. The reason we picked MRI again is it is because there is a part of some quantumness in the data that comes from these MRI machines. Of course, for example, it's very interesting to see that I didn't know about it before we starting the project, but actually the information that we get from the MRI sensors is not the image that we see at the end, but it's the Fourier transform of this image. And then we have to make this transformation to make into a brain image. So already you can see why quantum could be interesting in this type of, pipeline where Fourier transforms are also something, one of the things that we know how to do efficiently on a quantum computer, for example. So yeah, I think the more quantumness and quantum effects are in the use case, whether it is on the data or whether it is on, it can be both on the physics side, like because the system itself, is governed by quantum effects. It could also even be from the mathematics side. If the mathematics look more like quantum, mathematics, then this is where we think that using a quantum computer can be actually very useful to learn something that takes into account these effects and gives you better models and better solutions.
Thank you for that. And I would like to ask Grant in particular, do you think you have a very strong background in classical, let's say, machine learning? Do you think we need quantum machine learning in order to create beneficial, use cases? Or it is enough really to have maybe machine learning algorithms, classical ones, that are augmented maybe with data coming from a quantum computer, or even maybe just a quantum system, machine learning
what's
on quantum data.
Time horizon for this question?
Oh, sorry,
what's my time horizon?
Let's start with 3 years from now, and then 20 plus.
So obviously, the project that we have pitched is using data acquired on a quantum computer and using classical machine learning on top of that. That's where I think we're kind of at the point to do sort of the most transformative things with quantum computers. But if you think about, the landscape of classical machine learning at the moment, there are sort of three main problems. One is data. So we need to acquire data for, a lot of the applications that we see in, the news and like media. Data is not a problem. Language and image data are cheap, easy to come by. The internet is completely filled with them. It's not actually an issue. But when you start thinking about things like structural ensembles of individual proteins, this is data that is extremely expensive to acquire. Same with potential energies for individual molecules. These are very, very difficult data sets to build, and reducing the costs of that and then employing classical machine learning on top of that is obviously an opportunity. But then there are two other problems in machine learning that I think actually attract much more of the focus from the ML community. And those are optimization and representation, so the architectures of the neural networks that we actually use. And I think on a longer time horizon, there are really big opportunities there for maybe not necessarily more expressive neural network architectures, but things that are much more efficient. So transformers were mentioned in the last talk. Those are architectures that are extremely good, right? They're very, very expressive. They're underlying almost all of the modern chatbots. So, but the issue that kind of gets, many people know this. It's not a secret or anything. They require hundreds of billions of parameters. So they're extremely expensive to train, and they require much more information and in memory capacity than is probably necessary to actually produce the outputs that they produce. This is maybe a bit of a technical aside, but the way that transformers work is through this thing that's called an attention mechanism. And it was described at a high level in the last talk, but basically it's decomposing correlations and sequences into pairs. That's a really non-quantum way of thinking, right? Like doing a pair correlation function is a very classical way of looking at things. In quantum mechanics, we always have many body correlations. And there's really, I think, a lot of opportunity to exploit many body correlations and efficiently encode information and project it down to lower dimensional spaces using quantum representations. But it requires, entanglement. And that's something that remains hard. So that, I think, is a longer time horizon. But eventually, I do think there will be big opportunities there.
I really like the fact that you mentioned that some of the data that you considered when it comes to medical data, it's actually very expensive to acquire. So it's not the type of data that is freely available. And this is what also, to me personally, gives me some hope that maybe quantum machine learning will be good for medical data, especially patient data, which is very expensive and it's rare to acquire. And Kanav, can you share with us what is like, your favorite application, let's say, of, if you have one, of quantum machine learning in principle or in particular in health?
Okay, so I'll be super honest, not an expert in quantum machine learning, but the way we've been thinking about it is in the near term, people have been focusing on VQEs. And VQEs, like essentially even decent number of architecture for QML also gets built as variational circuits. So one of our research scientists has had a couple of really cool papers as to learn how to build efficient VQEs for machine learning, quantum machine learning. And we're sort of using very similar ideas for the applications that we are building at qBraid for the Wellcome Leap grant. As in, you do get these VQEs for chemistry problems, then can you use very similar ideas from the machine learning field that you develop that tell you which parameters are important for the circuit, right? So can you maybe throw away a few of the parameters that aren't as important and you can shrink down the circuits, right? And so the whole thing, you get to optimize the VQEs and you get to go deep into the optimization layer as well, the classical optimization part that allows you to complete this VQE loop. So these are the two main places. And the third is, as you get better energies for these chemistry systems, which again, to Grant's point, you can feed that into a classical machine learning model. So as you build better quantum database for the systems you want to study, that could, again, go back to building better classical or even quantum machine learning models.
I agree. And in principle, what would you say is like the main goal of your project? What is the main learning that you would like to achieve in it? We earlier had a question about the data loading, which obviously when it comes to quantum machine learning, it's still it's a very big question unsolved. So if I'm interested to hear actually from all of the panelists, if you can share what is the biggest thing that you want to learn and show from your project.
Yeah, I think the biggest thing for us would be to be able to generate better energies for the quantum chemistry system that we are trying to study. And what the main contribution for that I think we will be able to do is build this entire pipeline, how you start from a protein and go all the way to generating circuits that return better, meaningful outputs for you. And this is where our collaboration with QuEra is going to matter the most because we're constantly talking with them. And if we can generate better binding energy, then one of the most amazing experiences talking to a lot of pharma people and people in biology has been, it's like always a learning exercise. You talk to them, it's not what you think they want. That's so through better collaboration, that will be one thing. But we do think if we can just get you better energies of the system, then we will, hopefully biologists will find a way to use those energies in some places.
That's really nice.
So I think from our perspective, actually, the answer is very similar. We want to provide a very faithful representation of the energy landscape, but in a particularly violent and complicated setting, which is when chemical reactions are occurring. This is something that is very difficult to study in situ in proteins. So if we can kind of map out the landscape of, in particular, we're focusing on hydrolysis reactions at the moment. That's probably the main mechanism of energy transduction in cells. If we can capture the effects of the protein environment on that hydrolysis using VQE, then we hope that we can study actually the dynamical consequences and the fluctuations that arise from those reactions.
Iordanis.
Yeah, so I think the bottleneck that we need to solve if we want to do something on MRI diagnosis, let's say with quantum computers, is to figure out how to teach a quantum computer to learn something by itself of a size that we cannot simulate classically. So we really have to start training and using all the kind of AI techniques that we have in order to somehow figure out a way of making the quantum computer learn how to perform a task. It could be a diagnosis, it could be the reconstruction of the image, by using the most state-of-the-art AI techniques that we have, like reinforcement learning and all this type of techniques. And this is not really obvious, right? And especially because you gave us the challenge of doing something useful with more than 50 qubits. So first of all, we need to have more than 50 qubits. But imagine we have over 50 qubits, then, yeah, how do we learn how to do something useful? For example, by training, the simplest case, training a quantum neural network, let's say. It hasn't been done before at this scale. And I think there will be many challenges when we try to actually do it. But yeah, that's why we're here for. So I think it's possible.
I love the useful, emphasis, because I think that's super important, and this is really the goal of the program, is actually to show something that will be useful, maybe not tomorrow or in 1 year, but maybe in 3 or 5. Tommaso, what is your view?
Yes, I generally agree with all the previous statements. What I think will be the major challenge from QuEra's perspective is really to be able to implement hardware-efficient algorithms on our platform. So regarding Iordanis' comments on getting more than 50 qubits to work for basically realizing these types of implementations, what I can say is that for these type of platforms that we are currently working on, which are neutral atoms, they are sort of intrinsically scalable to more than hundreds or even thousands of qubits. That's not the end of the story. The other really relevant point is the fact that we have also we can program the geometry of our platform in such a way that the encoding becomes even more efficient. And this is particularly relevant for typically optimization problems or even quantum machine learning algorithms. So of course, I want to say it very clearly, so that the types of implementation are still sort of exploratory. We are developing a specific type of algorithm internally to QuEra, which is called the quantum reservoir computing, which basically boils down to a specific encoding of, let's say, an image, if we want to do classification, either binary or multi-class classification, into some specific features, either of the microscopic dynamics, which means the Hamiltonian of the system, or into the geometry of our qubit array. So these qubit arrays, as I said, can contain at hundreds or even thousands of qubits, and that's a good part. The other good thing is that we have very high controllability of their dynamics. So there are two different modalities in which we can run this type of algorithms. The first one is what is called the analog mode, where you basically control at the pulse level the dynamics of the parameters that basically constitute the Hamiltonian of the system. The other way is the other modality is perhaps what is most common to our panelists, which is the so-called digital or gate-based approach, which consists in basically preparing a circuit, a standard circuit that you can run and eventually optimize with techniques that both Grant and Kanav were mentioning. But the question is, if you want to do it well, you need to have a very good hardware. And this is perhaps the major challenge that we are encountering at the internal level within QuEra. I would say at the level of the project, more broadly, the first thing that we are achieving is really getting up to speed with in bridging the gap of communication with our quantum chemistry colleagues. As you can understand, so we are really on the opposite side of the spectrum in terms of the applications, which is really the formulation of the problem at the hardware level. Typically, when we speak about a specific domain or domain-specific applications, we really need to start learning the language in order to make progress. And I think this also reconnects to what Kanav was saying at the beginning.
Thank you for that. And I agree. And I wanted to ask you if anyone want to share in the last few minutes before I open for questions, if there are already any learnings that you found in this challenge program, something that you can share, and maybe something that is translational that other teams can also adopt so that they can develop, successful applications.
Perhaps a very quick comment. So we are involved in so many projects that it's clear that there is really a continuous learning. And the learning is really taking place in the first phase, because one thing that perhaps is worth reminding is that the Wellcome Leap is really a multi-phase project. So there is phase 1, phase 2, and phase 3. The real realization of this algorithm in the experimental platform will really take place at the very end of the program. So from an hardware provider like QuEra, the first phase is really on defining what is sort of the budget of these calculations, of these computations. So estimating the resources that are needed in order to be able to efficiently produce and eventually realize these algorithms on the machine. Now, we understand that we also need to sort of teach, in a sense, some of our partners on the capabilities, the current capabilities of our machine, as well as about the future capabilities of the machines, both in terms of analog as well as on digital. On our side, the major achievement, again, is the learning of the partners' expertise.
Yeah, no, this is very important. Maybe one thing actually Tommaso also said, it is that what is clear even with the 3 months that we started working is that if we really want to make an impact and find something useful to do, that we need to work in interdisciplinary teams. Like, it's extremely important to have the experts of the domain, the experts of the quantum hardware, the quantum software. And this is the only way to make sure that we're solving the right problem and not what we think is the right problem, right? And this dialogue between, okay, what really needs to be done and what are the techniques, and figuring out how to match the two, I think and this is why this Wellcome Leap is really remarkable for me. One of the main reasons is the fact that we put together teams that have all this expertise and can work together. Yeah, and I'm also looking forward to see what the other teams are doing as well. And I think this will enhance and enforce what each one is doing as well. Yeah.
Yeah, one thing that's sort of, I think, kind of interesting and unique about our team is that it has a lot of people who have strong backgrounds in quantum chemistry, but then moved to quantum computing. And so they're really fluent in both. And that has been, I think, a unique advantage for us. And one of the things that we've done early on is just sort of try to understand, both on the classical machine learning side, this procedure of transfer learning, and also on the VQE side, how circuit depth affects the solutions that we get for VQE. Unsurprisingly, deeper circuits are better, but one of the things that's been sort of interesting about this on both notes is that really targeted data selection can have a huge impact on the quality of the results. And this is something that we're trying to kind of formalize so that we can target the energy calculations that we will do on a quantum computer and try to generate kind of optimal selection of data. So hopefully we can kind of continue to our project is at some level all about compression. We need to compress the Hamiltonians. We need to compress the amount of data we require, and so we're trying to build all of that into the framework.
Right. I'm not sure how much we want to share, but one thing that at a very high level that has been really cool to see is many times you come up with these ideas and they're kind of localized, but having many different teams present on a single call, you get to see how ideas which seem local now are applicable in different areas that you didn't expect. So that has been something really cool. Like any innovations you see in a VQE, they automatically get applied to LAS UCC and QBE all together. Or similar ideas, you come in LAS, they automatically gets applied to QBE. So I think that's been one of the coolest thing working on a Wellcome Leap grant is multiple teams working together, and sometimes a local impact shows up much bigger when you put it together in the entire pipeline.
Thank you. So to summarize, maybe for near term, we need to really compress maybe the problem, the data, and also have really close interactions and collaborations with different teams, and in particular with the domain experts, so to come out of our comfort zone of quantum computing algorithms. Thank you very much to my all-star panel, and I would like to open for questions if there are any questions from the audience. There is a question. Okay, a few.
Thank you. Hi, yes, thank you very much for that. That was great. If it's okay, I have one question for Tommaso and one question for Iordanis. So for Tommaso, the only other time I've ever heard anyone mention reservoir quantum computing is with another quantum computing company called Quantum Computing Inc. They've got two kinds. One is entropy and the other one is reservoir. I was wondering if you can just talk a little more about that. I don't know if you know this company or what they're doing with the reservoir quantum computing, but maybe talk about what you're doing with it. And if you do know, maybe if there are any differences, they're working with photonic, and I know that QuEra is neutral atom, so there might be something there. So reservoir quantum computing. And then for Iordanis, there is a chorus of skepticism when it comes to quantum machine learning. I wonder if you could maybe tell us what the most convincing evidence is that you've seen so far from a technical standpoint that actually gives you reason to be optimistic and shows evidence that it will actually be successful and useful, perhaps not in the near term, but maybe somewhere in the midterm, so that we're not waiting 20 or 30 years just to see anything happen there. Thank you.
So perhaps I can start. So first of all, thank you for mentioning this other company. I'm not aware, so I would be happy to connect with you after the discussion, and you can point me
It's not my company, it's another company.
No, I understand, yeah, the company that you mentioned, but it's not yours. So regarding the type of algorithm that we implement, I want to sort of emphasize the fact that these are sort of still exploratory applications. The way this quantum reservoir computing works is basically, let's say that we want to do classification, so we have an image of a horse or a cat or something else, or even doing, I don't know, digit classification from the MNIST data set. Then what we do is basically we compress and just keep the most relevant features associated to that image, and then we want to encode those features into our neutral atom array. So now the question is, how do we perform this encoding? Okay, the encoding can be done in multiple ways. There are two main ways in which you can encode the data into the array. The first one is to basically encode information into the local energies of these qubits. So you have internal states of the atoms that basically work as the basis states for your qubits. And then you have certain energy shifts or energy differences between the two internal states. Now, this can be local in the sense that it can vary from atom to atom, and this will provide some information regarding the features that you are interested in encoding into the array. The second different way is to basically work with the positions of the atoms. This is also relevant because the interactions between these qubits are basically distance dependent. So this means that by changing the position of the atoms, you are really changing the effective dynamics of the system. Once you fix or you encode the data, you then run your native Hamiltonian or your native dynamics of the system, and finally get some measurements. When you get measurements, so of course you need to repeat in order to get enough statistics, you can just run a single layer of basically a single layer neural network and extract the relevant information of whether the image you were talking about was a cat, a horse, etc. So the main advantage of running this type of algorithm is that you don't need basically to train the quantum side of the algorithm or the reservoir, the neutral atom array, and so you avoid basically an essential feature of classical neural networks, which is basically back propagation to update the parameters of your neural network. So this is a sort of smart way to make the best use of the resources that we have currently. So the idea is and then practically you can implement this algorithm first by using an emulator, and then our neutral atom array, which currently works within this analog mode and is scalable, and actually it can get up to 256 qubits. So
Thank you,
much more than.
Thomas.
I'm sorry, so I was
It's all right.
just super excited to explain the
I
algorithm.
understand.
Well, I cannot be very short either with that question, but okay, I will try my best. So for me, it is quite simple, right? So my goal is to figure out what is kind of the final frontier of AI, let's say, right? And what is intelligence? Intelligence is just the ability of some agent, some system, right, to perceive its environment and learn how to do some tasks, okay? So how well we can perceive the environment and the world around us gives us much more power to be able to learn how to do tasks, right? So to me, it's very clear that if we really want to get all the way to the ultimate power of what these agents can do, they have to be able to deal with quantum effects. You know, we can do 99% of the things in the world without, you know, ignoring quantum effects. But the 1% that we need quantum effects is what gave us, you know, semiconductors and lasers and all of these things, and biology, like molecular chemistry. So to me, it's kind of clear in my mind that if I want to understand how much can we push AI, we need to enable our agents to be able to perform quantum computation, quantum calculations, quantum sensing, and all of these things. So to me, it's very clear. Why are there so many skeptics? There were many skeptics in AI for decades, right? There are fewer now because we reached the point where we can actually do something useful, right? We are not exactly there yet on the quantum side, right? I think we're getting closer. I think Wellcome Leap would help a lot to figure out how to use quantum AI in life sciences. But you know, what we see so far in the small scale experiments that we do, right, is that there are advantages that we get, right? It's very difficult in machine learning to prove that, you know, my model is the best at anything you can ever come up with to solve the same problem, right? It is clear. But to me, it's also clear that adding quantum capabilities in the toolkit, in the AI toolkit that we have, will push us forward and will get us to the best possible results. Yeah.
Thank you. On this positive note, I want to thank. Okay, there is a question. Please, two even. Okay.
I'll just speak up. Is there any advantage to trying to run some of your experiments just with a quantum annealer, a simplified experiment on something like a D-wave machine?
It's for me? Yes, I guess.
For parameter optimization, it's probably worth trying. I think
You can, of course, try. I mean, we're not saying that you should not try other approaches. It would be worth actually trying. What I'm saying is that by employing the type of algorithm that I was mentioning, what we achieve are basically very similar performances that you can achieve also with other classical algorithms. So for certain specific tasks, we see really similar performance with much less effort in implementing all these neural networks. So this is also some sort of degree of efficiency, if you want, in employing this algorithm that needs to be taken into account when you really want to deploy more complex tasks.
Thank you. Thank you very much.